Hello, thanks for clicking. Welcome to another Nargilus 2 production. Today we're going to learn to integrate by parts. Okay, so basically what we're going to do is we're going to learn how to integrate a product that right now we cannot integrate. So you can't use substitution. There's no rule that you can use for it. We're going to learn how to take two functions that have been multiplied, integrate them, if there's no other rule that can be used. Okay, so let's get started and we'll see what exactly that means. So again, the goal is to integrate a product of two functions for which substitution or any other method does not work. So a good example of something that requires integration by parts would be this: the integral of x times e to the x dx. So again, substitution does not work on this. There is really nothing that you can do with it, right? X times e to the x. You can't split them up because that's not a property of integrals. So the question is, how would you integrate something like that? Okay, so to do this, you're going to need integration by parts. So integration by parts is actually based upon the derivative product rule, right? The product rule for derivatives. So let's write out the product rule for derivatives, and then we're going to work from there and see what we can do with it. So the derivative of two functions u and v, u times v, would be leave the u, right? We're going to leave u, and then we're finding the derivative of v, plus leave the v, and then the derivative of u. Okay, so now we have those. That's our product rule for derivatives. But here's the thing. I don't want to derive this thing. I want to integrate it, right? I want to integrate it. So I'm going to integrate on both sides. It's an equation. I'm allowed to do that, right? Whatever I do on one side of an equation, I got to do on the other. So I'm going to integrate on the left, and then I'm going to integrate on the right. Now, when I integrate on the right-hand side, I have two terms that have been added. So the properties of integrals allow me to integrate each one separately. So I'm going to do that. Okay, and I get this. All right, so now one of these integrals I can simplify. It's the one over here on the left. I'm asking you to integrate the derivative of u times v. Well, the integral of the derivative, they just knock each other out, right? If I derive something and then I integrate it, I get back to where I started. So where I started was u times v. And then over here on the right, I'm going to keep everything the way it is right now. Now, what I'm actually going to do is I'm going to take this equation, which is basically is, and I'm going to solve it for this term here in the middle, the integral of u dv. So I'm going to subtract the integral of v du on both sides of my equation, and I get this equation. The integral of u dv is equal to u times v minus the integral of v du. This is the equation to integrate by parts. Okay, so the integration by parts, it's actually an equation or a formula that you're going to use to actually go ahead and integrate these functions. All right, so now the question is, how does this thing even work, right? So let's go to the next slide and we'll talk about how it works and how it would apply to something that looks like this that I actually want to integrate. So using the integral, you're going to break your integral up into two parts. So let's say I wanted to integrate x times e to the x dx, just for the sake of saying we're going to try to integrate it. We're not going to integrate it, but it gives me an example to work with. Okay, here's my parts formula. The integral of u dv is equal to u times v minus the integral of v du. So here's how this thing works. Basically, what we're going to do is we're going to take this integral or the integrand and break it up into two parts. We're going to break it up into u, and the rest of the thing we're going to call dv, which is basically this integral on the left, right? The integral of u dv. So part of the integrand has to be u, the other part has to be dv. And then we're going to apply this formula to be able to rewrite the integrand with a new integral. Okay, mainly the second integral that we see here. All right. So once you pick your u will be derived. You're going to derive u. And then dv will be integrated because you got to integrate dv to figure out what v is equal to substitute it into this formula. All right? So if you choose correctly your u and dv, the resulting integral that you get, which is this one, should be easier to calculate than the previous integral you had at the start. Okay? Now, the easiest way to do this is to pick what u will be, and then whatever's not u becomes dv. So how do you choose u? Well, there's a lot of different ways that you could say how to choose u. I use the acronym LIPIT, LIPIT good. Okay, and this is what LIPIT stands for. So to choose your u, the top of the list is a log. If you see logarithms, you should definitely pick that as a u. Inverse trig is second, which seems a little bit shocking. Inverse trig seems to be a pretty random choice, not to mention its derivative rules are very, very strange. Okay. Polynomials, so like x or x squared or x plus 5 would be my third choice. And then down here, exponentials and trig really are kind of interchangeable. Both of them are what I would consider to be garbage choices. They're not very good choices at all, okay? Because neither one of them are easy to work with, all right? So an exponential function would be like your e to the x or 5 to the x. Trig obviously would be sine, cosine, tangent. Logs would be log of x with base 2 or natural log x, something to that effect, okay? So this is how you're going to choose your u, all right? So up here in my example, I'm not going to do the whole problem here because we have plenty of problems to try. If I were to choose u, x is a polynomial, e to the x is an exponential function, so I would choose x as my u, and then everything else would be dv, and then I'd work from there, okay? That's how that would work. All right, so let's try it. And we'll try it on a couple of examples here and see how it goes. All right, here it is, x e to the x. So we're going to use parts to do this. There's no other way to do it. We'll write down the parts formula here. The integral of u dv is equal to u times v minus the integral of v du. And I'm going to pick u, and the rest of this integral will be dv. I'm picking u by LIPIT, LIPIT good. So again, my choices for u and dv. So x is a polynomial, e to the x is an exponential. I'm going to pick x for my u, which means e to the x dx will be dv. Now, here's how this works. To apply the formula, I need to know what u is, v is, and du is. So I can find du pretty easily by deriving u. The derivative of u is derivative of x is 1 dx. Okay. And then to find v, well, I know what dv is, so I'm going to have to integrate dv on both sides to figure out what v would be. The integral of dv is v, excuse me, and the integral of e to the x is e to the x. Oops, no dx, I don't need that. All right. So now we're going to take and we're going to plug it in. So the integral of e to the x dx can be rewritten as u times v, x times e to the x, minus the integral of v, e to the x, du is dx. So now my resulting integral should be easier than the one I just looked at. So the one I started with was x e to the x, which I could do nothing other than parts. But now I have an integral of e to the x dx, which I can just do, right? I can just integrate this thing. So that would be x times e to the x, bring that down, minus the integral of e to the x is e to the x plus c. And that's the right answer. That's the integral of x e to the x with respect to x. Okay? That's how this works. All right, let's try one more here. Let's try x cosine 3x. So again, another product where you really can't do anything with it, so we're going to use integration by parts. The integral of u dv is equal to u times v minus the integral of v du. Okay, so I need to pick a u, and then the rest will be dv. I'm picking u, by Lippitt. Lippitt good. All right, so my choices are x is a polynomial. Cosine 3x is a trig function. So that means x will be my u. Cosine 3x will be my dv. Cosine 3x dx, right? The rest of it, all this, is going to be dv. And x is my u. Okay, that splits up my integral. So now the integral of x cosine 3x dx is equal to, let's see, we got to derive u. Derivative of u is 1 dx. We got to integrate dv. Integral of dv is v. Integral of cosine 3x. You need substitution for this. So I could let w be 3x. dw is 3dx. And I need a 1/3 for Beach Boys. So this is 1/3. The integral of cosine is sine. And then I'm going to throw the 3x back in there. All right, so now I'm going to put all this in there. U is x. V is 1/3 sine 3x minus the integral of v. So I'm going to put the 1/3 outside. I don't need it. It's a constant multiplier. V is then going to be sine 3x because I put the 1/3 outside. Du is dx. So now, it should be easier than it was before. This is easier than it was before, and now it's even possible. So I'm going to integrate sine 3x. So again, I'm going to let w be 3x again. dw is 3dx. I need a 1/3 there. Okay. So now we have 1/3, if I clean up the first term a little bit, x sine 3x minus 1/3. This is going to be the, I need a 1/3 there for Beach Boys, another 1/3 from that. The integral of sine w dw. The integral of sine is minus cosine. So this is 1/3 x sine 3x minus 1/3 times 1/3, 1/9. The integral of sine w is minus cosine w, but w is 3x. I'm going to put it in there. Plus c, and then these two negatives will make a positive. So that's 1/3 x sine 3x. Negative times a negative is a positive, 1/9 cosine 3x plus c. And that's the right answer. Oops. Okay. And that's how integration by parts work. All right. Check out the next video for some more integration by parts. As always, thanks for clicking.